Mm-hmm.
Okay, everyone. Good afternoon. Welcome to the afternoon. Yeah. Welcome to the afternoon session. So the first speaker in this session is Henrik Bosch-Virchow from the Universidad Federal de Rio de Janeiro, and he will talk about spectral form factors and the hadronic structure functions from a deformed EDS model.
Thank you. I would like to thank the organizers for the invitation and for this very nice conference. So this morning we have some talks on magnetic field effects and temperature and density. I'm going to talk about some recent results on zero temperature, zero magnetic field, and zero density, which are related to these very basic facts in particle physics from deformed ADS model, which is inspired in the ADS-CFT correspondence. These are my collaborators in these works: Martin Contreras, Eduardo Caposoli, Danny Lee, and Alfredo Vega from these places: Chile, Rio de Janeiro, China, and Chile. So just a cartoon. So in ADS space, you define some theory in this space, maybe 5-dimensional. That's the case here. Maybe 4-dimensional also. And you have a gravity theory in this side of your correspondence. And then these theories are related to quantum field theory. These are classic gravity theories. These are related to quantum field theories in this space, maybe Minkowski or Euclidean, depending on the signature of how do you define your anti-de-Sitter space. So usually I'm going to talk about this ADS-5 related to Minkowski in 3+1 dimension in flat space. Okay. So this is the typical metric in ADS space. So looks like a flat metric here, right? But we have so this T and X are the usual Minkowski. So this is the Minkowski signature. So these are the usual T and X of Minkowski space, and this Z is the extra coordinate. So this is the additional coordinate that we are using to do holography. And this is the curvature, the warping factor. L is a fixed ADS radius, which is usually put to 1. And Z is the coordinate related to this part of the metric, which is singular, right? So this is singular for Z equals to 0. And this is a characteristic of the ADS space. This is the simplest coordinate description of the ADS space, which we are going to use as the startup to propose models to describe QCD-like theories. And these are related to usual Minkowski or Euclidean space, just depending on the sign you put here for the T part, okay? So I will start with the very simple examples relating holographic theories for QCD, very approximated theories. The most well-known model is this called Hadron model, was inspired by this work of Polchinski and Strassler. And I did some work with Nelson, which presented this morning. And you start with an action, right? This part of the action, X, is the flat space. So this Z is the extra coordinate related to the curvature of the space. So you have this square root of -G, which is a characteristic of curved space-time. And then you have the Lagrangian, the usual Lagrangian of the fields. So usually we would work in 5 dimensions. So this is 4+1 dimensions. This is, again, the ADS metric. And the hard wall, the difference of the hard wall from the usual ODS is that the Z coordinate, which usually runs from 0 to infinity, is an infinite space. The hard wall, the difference that we introduce a scale called Z maximum, for example, which defines a size for this ADS space. And this size defines an infrared scale, which can be identified actually is the inverse Z max. Z is the inverse of an energy, so it can be identified with 1 over lambda QCD, for instance. Okay, and in this work we did some application calculating global masses, and this was also extended to other hadrons. I will talk about also these in these works. I'm going to say more about this today. This is the other very well-known model called the soft wall, KKSCS for the Karch and the other authors. So instead of the difference from the soft wall to the hard wall is that instead of cutting the space in this Z maximum, the infrared scale is introduced, putting the exponential, the decreasing exponential of the Z coordinates. Okay, so this K plays the role of an infrared scale, right? So here the metric is pure ADS. This is let's say the advantage of this model, right? And this also pure ADS, but we modify the space, cutting the space in this region, right? And then this soft wall model was applied, for instance, initially for vector mesons, but does not work very well for other hadrons unless you do some modifications, as the one I am going to talk about here. So this is the model I'm going to talk about for studying spectra, form factors, and deep inelastic scattering also. So this is one of the work we have done, right? So we start with an action, right? Like the usual for ADS, okay? Here is the ADS metric, and this deformed with what we call deformed ADS is that we put the exponential similar to the soft wall with the opposite sign here directly in the metric. Okay, so we put no exponential here, but we put an exponential here. So this is very similar to the soft wall, but there are important differences. With this model, we can find a discrete spectra for all particles, all massive particles, which is not the case of the soft wall. In the soft wall, you need to do extra modifications to obtain this. So usually, we parameterize this warp factor and exponential through this function A, which will appear in many transparencies, in many slides. Okay. For instance, if we start with global, which is not the most interesting case, but is an example here, we just put the Lagrangian of a scalar field, right? So using these functions here, we can find the equation of motion, thus the regular equations of motion in terms of A, right? You can find solutions in 5 dimensions for the fields. So in 4 dimensions, it's just plane waves, and the Z part is the important part from the holography, right? We can factorize this function A and have a function psi, right? This equation can be solved in some cases, and using some prescriptions. Usually, we consider Brodsky-Teramon prescription for globals, and we find that this is also important to mention. This is a 5-dimensional mass, or a mass for the field in 5 dimensions, right? Which is not the mass of the particle we are measuring. Okay, so in this model, it's possible to relate this 5-dimensional mass with the spin J of the globe ball on the boundary on the 4-dimensional theory. These are for even J or odd J. Right, we have these relations, and these are the red trajectories of these particles. You can see that these dots are masses. You can see that they are not linear, right? These are for the even and for the odd cases, right? These are the masses we find. Okay, so this is not very good actually. This model produces better results for the particles, actually. So for scalar mesons, we use the usual ADS-CFT prescription to relate the 5-dimensional mass with delta, which is the conformal dimension of the operator that you are describing on the boundary, and P is the P-form index. So in this case of a scalar, P is equal to J, the spin, which is equal to 0. And we want to describe scalar mesons. So the quarks, the canonical dimension of quarks are 3/2. So a meson is just the double of these. So a meson has dimension 3. So if you put this in this formula, you find that the mass square in 5 dimensions is -3. Which is allowed because when you quantize fields in ADS, you have the possibility of tactile field actually to a certain bound, and this bound is not violated by this condition, right? And then we consider here the same action as that for balls, a scalar action here with this 5-dimensional mass. Okay, so these are much better results, right? We have these dots and the squares. The squares comes from PDG, right? So our model really produce a linear red trajectory. So these are the comparisons between the masses. We have some good masses. These are the errors in the comparison. Okay. So this is also the case for vector mesons. We also start with this ADS prescription. In this case, the spin is equal to 1, so we have a 1 form. Also, the quark has dimension 3/2. Again, the meson is the dimension 3. And because of the form here, we have the M5, the 5-dimensional mass here is 0. So this will modify the analysis, right? And then these are our results for the whole meson family, for instance. Okay, these are actually, in this particular case, this is exactly the same result for the soft wall. So the soft wall, the pure soft wall has exactly this trajectory here. So this model, this deformed ADS model coincides with the soft wall, but just for this case of vector mesons, okay? So these are not very good results, but reasonable results. Okay, and then we move to baryons. So we consider the Dirac action in 5 dimensions, right? And here the Z is hidden here, also the minus sign of the G. And then that A that deforms this same A we are using, deforming the metric, right? So this actually comes in the G, which is I didn't say that's the determinant of the metric. So changing the metric moves this, change this square root of G. And this is actually for baryons or fermions in general, you have 2 equations because of the linear aspect of the Dirac equation, but you can improve to a second order equation, and then you have 2 equations. for the right, what we call right and left modes. Okay. So in this case, the ADS-CFD prescription is a little bit different. The modulus of the 5-dimensional mass is related to delta the dimension -2. So we have for spin 1/2 variance. We have a quark with 3/2, and then a baryon with three valence quarks will be 9/2. And then we find M5 to be 5/2. Okay. Here is also I am also including the value of the K, which appears multiplying Z in the deformation of the metric, right? I didn't mention before, but this is let's say, negative point of the model. For different family of particles, we need to use different values of K. Okay. So this is the K. This is adjusted to give a better fit of these masses. So this we see that we have a reasonable trajectory here. The errors are not very high. Okay. So these are for variance of spin 1/2 compared with PDG. We can also extend to variance of spin 3/2, and then you include one spin extra spin, so your dimension goes to 11/2, right? And then your 5-dimensional mass changes also to 7/2. This constant here is exactly the same as before. In this case, it's possible to do this, right? And this is these 3 dots are our points, right? We have some high speculation here that these errors are very high, right? And we realized that if there is one baryon missing here in this picture, then we shift these masses, and then the masses will the mass that we are calculating compared to this one from PDG will be much better if there is one missing particle here, which is this triangle. But this is just a speculation. Okay, so we can also goes to higher spins, 5/2, right? In this case, the M5 will be 9/9, with the same logic, right? And these are our results, right? Compared with PDG. So these are good masses. The constant K is a little bit less than in the case before. Okay, not the same, but a little bit less. Okay, so now I move to deep inelastic scattering, and this was we need to discuss this variance to do this application here. So this is the typical deep inelastic scattering. You define the Bjorken parameter, right? And then you want to calculate some amplitude m of corresponding to this process, where the x is something undetermined in the final state, right? And the usual deep inelastic scattering is done using the optical theorem and the Compton-Ford scattering. You relate that amplitude to the amplitude of a photon, a virtual photon with the proton going to a virtual photon with the proton, like diagrammatic like this. So actually, you can define a hadronic tensor, this object. This is our standard DIS analysis in terms of these currents, J mu, J nu, right? And using Lorentz covariance properties, you can show that this hadronic tensor, W mean U, it can be decomposed if these are unpolarized at the scattering in 2 terms. One is proportional to this F1 and the other to this F2, which are the structure functions. which are functions of the Bjorken parameter x and q squared. Q squared is related to the virtuality of the photon. And they have these behaviors in terms of the Lorentz vectors that you have. P mu and P nu are the proton momentum, right? And K nu is the photon momentum, okay? Eta mu is the metric, the Minkowski metric. So this is what you can do with unpolarized scattering, and we are going to use the holographic model to obtain these F1 and F2 structure functions. Okay. This has been done before in the very original work of Cauchy and Strassler, 2003, for scalar and fermionic particles using the Hardwell model. Was just one of the inauguration works of the Hardwell model. And they worked in three regimes, in the large x, small x, and very small x. I'm going to show only calculations in the large x regime. I'm going to show the results. And Maldacena wrote some comment on Nature, mentioning that this work of Cauchy and Strassler allow us to interpret the string in higher dimensions as something that we don't see directly. We just see some projection in 4 dimensions, which are the particles that we actually see. So this calculation of Cauchy and Strassler allow this nice interpretation. So you does not need to interpret string theory in 10 dimensions directly. You just, what we see is just a projection like this in the screen, right? And this projection is what we see for space-time dimensions. So again, this is the 5-dimensional action, right? And again, this is the formed model, the formed metric with the same A as before. So we studied the spectra, then we moved to the DIS, and then after I'm going to show the form factors also. In the DIS, we need an interaction between the fermions and a photon field, which is described by this electromagnetic field, which has an analytical solution in this case in terms of hypergeometric function. And then the baryonic states, again, the Dirac equation in 5 dimensions, right? That so we can find a solution for the initial hadron and this index I, and the final hadron with a call X here, right? And as I said before, for the baryon, we have the prescription of ADS M5 for fermions will be the canonical dimension -2, but actually to fit our data here, we actually need to introduce some phenomenological anomalous dimension here that I'm going to show the values. So these baryons need a numerical solution in this model. So I'm going to present some shapes here. Correspond. This is the ground state. These are the first excited states for the baryons, okay, that we use to calculate with some adjustments of the constants, right? And then we want to calculate this current J, yes, as an interaction between the 2 states, the final and the initial state of the hadron, and the phi here, phi mu is the electromagnetic field, okay? So actually, what we have is this very important expression here, which summarizes what we are calculating in the DIS from the holographic point of view. We have this psi A, psi X representing the initial and final baryon, and this B is some part of the photon apart from the plane wave and the polarization of the photon. So what actually we need to calculate is to do this calculation numerically, because we only know psi I, psi x numerically, but we know B exactly. So we need to calculate this integral, right? And this integral, thank you. And this integral is just what we this input here, IL and IR, right? So once we know these integrals, we can calculate this interaction, right? And then we can go to the hadronic tensor, right? We need some adjustment with some effective coupling here, right? So these are the I's, L and R, the integral I just mentioned, okay? I'm going to skip some details. And these are the functions that we obtain for the structure functions F1 and F2, right? So they are given in terms of that integral that I mentioned before. I repeat it here, okay? So we know exactly the behavior in terms of the Q square and X, right, for the F1 and F2, right? And in terms of these integrals, which are numerically in this model, right? And for instance, we can take this high mass here and high Q here, and X go into 1, for instance, we find this kind of Cullen-Gross relation, right? But not for X. Usually, this Cullen-Gross relation is fine for X equal to 1/2. Here we are going to we find this for X going to 1. Okay, these are some details for the 5-dimensional mass that we need to fix. So for some values of X, which are going to compare with experimental data, we need to use some different values for M5 and different IR scales for the fermions, the different couplings, and also different anomalous dimensions, right? This is a little bit high, but we need that. And use this anomalous dimension here, okay? So this is the comparison with experimental data for 3 values of X. This is the F2 structure function. F1 we can obtain in the sequence. So we have X equal to 6.5, 7.5, and 8.5, and data from SLAC and BCDMS, right? And this is, as you see, this is the case of X equal to 0.85, which is the better result for us. So actually, we are following the Pochin-Strassler prescription. In this kind of calculation I'm showing is more suited for large X. So it's actually working very well. So as we go to smaller X, we are escaping from the experimental data. Actually, for small Q, we are not very bad, but when we grow Q, we are losing data, right? So typically, we would need a second approach for small X, but for large X, seems to be very good, okay? And this is the comparison between F1 and F2, which is close to 1. Okay, so how much time do I have? 1 minute. So I'm just comment that it's also possible to obtain form factors. So we studied the pion form factors. I will skip all the details. Well, it's the same model, right? So we also need a numerical study, right? So we have the standard analysis with the canonical dimension for the meson, which is equal to 3, right? And this blue curve is our results, which is not very good, right? These are other calculations, go much higher than ours. So this canonical analysis in our case does not present a good result. These are some comparison with experimental data. Okay. We also, in order to improve our results, we also consider again the canonical dimension, but this time we modified the scale, the infrared scale K, which was a constant. Now we assume it to be a function of K, right? Of the momentum of the photon, right? And we usually just the linear function, which was fine. And then our results improved to like a mean value of all previous calculations, right? So this is much better. And this is the comparison with experimental data, which is much better also. We are missing this point, okay? But it's much better. And a comment, yes, I forgot to mention that it's possible to connect with light front, right? Just I'm going to talk here. One negative point of our previous analysis that this form factor, we have some expectations about the high Q limit, which should be 1 over Q square, right? But here in our analysis, if you use the canonical dimension delta equals 3, we are not going to find, right, 1 over Q square in our model, right? But in Brodsky-Teramon model, in light front wall, soft wall, they use it or find, I'm not sure how they did that. They have delta equals 2 for a meson, right? So they have this behavior, right, in their model. You can see the original work in 2008. They have a lot of works and reviews. I just mentioned this most recent one here. So they have these nice pictures. In our case, when we modify the infrared scale to be a function of the momentum of the photon, then we have a form factor that has some more interesting dependence on Q. And so then in this case, we reobtain the expected 1 over Q square regime. So actually, this is what I'm going to talk. So we are going to extend this to other situations. Yeah, maybe very interesting cases mentioned before. So that's it. Thank you.
Thank you. Thank you, Harry. Okay, now it's time for questions.
One sort of a big issue in sort of heavy ion collisions is the relationship between parton density, sort of if you want the initial stage, and the initial entropy density of the quark gluon plasma. Can you guys say something about this? Have a constraint, since
actually, I was not considering density and temperature, but it's possible. Nelson talked about this a little bit in the morning. Is it possible to have some holographic description of heavy ion mesons? But I'm not sure if this corrects this situation you're mentioning, but is it possible to do that, also including finite density effects and magnetic fields, also rotation, as Nelson mentioned?
You don't have quarks at all. You don't have partons, right?
Yeah, is it possible to have quarks? This usual description, we have just bound states, which is let's say the most easy part of what corresponds give us. But if you have essentially is the point, if you have a closed string, you have a bound state like a glue ball or hadron or meson. But if you have an open string, the end point will be a quark in one side. So if you want to describe a quark, like a quark which was liberated from the heavy ion, for instance, in the medium. You can do that with an open string going around this medium. It's possible. I didn't show that, but it's possible.
But here it was only bound states and
Here,
closed strings.
I just went to in the direction of bound state.
Okay. Oh, we now have a question from our online participant from Zoom. So basically, his question is whether it's possible to calculate the hadronic contribution to muon anomalous magnetic moment G-2 using either deformed ADS or software model.
This is an interesting question. I don't know how to do that. I have been thinking about how to consider this magnetic anomalous effect. This is a big question. I don't know how to do that, but it's an interesting point.
Thanks for a nice talk. But about the pion form factor, which is, you have parameters free, or what you fix to fit your pion form factor? What is too much parameters free you have?
Okay. Yeah.
Thank you.
Right. You want to know how many parameters? Numerically, right? So we have the model. Okay. No. I didn't mention the radius. No, the radius we obtain from data. We obtain from the model. Okay. Good question. I will skip this. We fixed this case, right? Okay. So we have we were not able to find the best case, let's say. We put this at values. Then from these estimates, we can find with some variation here the rate, right? Sorry, this is not very good, right? And this is the well, let's say improved model, where we have the same constants here, but now we allow the generalized constant, let's say, to be a function of K, right?
Yeah.
And then in this model, with this radius, with very good agreement, right? Right. What will be obtained, right?
Okay. Then if you go so far in momentum transfer, you think you continue his patamar like that, no?
Yes.
You believe you do that? Because, you know, Ake try go so far in momentum transfer for the light mesons, no?
Yeah, this is what I was mentioned, right? This is asymptotic behavior, right? For momentum transfer. This is the expected result, which Brodsky and Ramon found with some, I don't know how they did this delta equals 2, okay? Yeah.
Okay.
Yeah.
Now we have a question from Stan. Stan, please.
Hi, I'm calling from Menlo Park, California. Hope you can hear me. I have a cold. Sorry I can't be with you and Leo. We've been wonderful. I'm just, I'm wondering if you've done a detailed correspondence with light frontallography. The basic point is that the variable z in the fifth dimension is actually holographically dual to an invariant variable zeta, where zeta squared is b perp squared x1 minus x. And that leads to all sorts of wonderful results, super conformal results, supersymmetry between meson and baryon trajectories, the same slopes in N and L. You also get the running coupling at all scales, form factors with which do obey dimensional counting rules and so on. So it's a very simple ansatz where you just notice the correspondence between z in the fifth dimension and the variable zeta in 3+1 light front QCD. And it's crucial to use light front, which is frame independent and causal. So I'm just wondering if you've looked at this and so on. It's a well-known results, and I don't know if you've done any comparison, but certainly this correspondence between the fifth dimension z and zeta and in physical lifetime time. Quantized theory is really remarkable and simple. And I think maybe you could look at to see how that would work for you as well.
Okay. Yeah, to be fair, and Guide Peramon, they actually show that these holographic models can be interpreted or improved, maybe in a light front description that he was explaining. I have read some of these works. In this case, they found this delta equals 2, but I don't know the details, but okay. This is very interesting because they have found many results in this light front approach, which is kind of improvement of the software model. Right?
That's right. Yeah. In fact, I should mention with just one parameter as well, in addition to the quark masses, of course, and it goes through virtually the entire particle data book. It's mesons, baryons, and also the tetraquarks. And also a new insight too is that baryons are the dominant Fock state is quark diquark, and this leads to also many results for the baryons too. And you get the Dirac form factors, the Pauli form factors, and so on. So I think it'd be very helpful to look at a correspondence between your results and the light front holographic results.
Okay, thank you. Yeah, that's correct. Exactly. These many work they have done, they have populations of form factors and spec, a lot of
structure functions, polarized structure functions, all sorts of interesting things. Yes.
Thank you.
Thank you too.
Okay, I think due to time constraint, we should proceed to next talk. Thank you,
Thank
Henry.
you.
Okay, so the next talk of this session is from Alfonso Balan and Bayona. We will talk about a confining holographic QCD model from vector mesons and nucleons. Actually, four vector mesons and nucleons.
So, can you hear me?
Yeah, go ahead.
Okay, can you hear me well? Okay, just let me get the point. Okay, first of all, I'd like to thank the organizer of this very nice conference for the opportunity of for the invitation, opportunity of getting involved and getting to know more about this very nice subject of Light-Cone or the light front QCD. My work is somehow has some connections. I think that as Stan Brodsky has already mentioned, there are some connections between holographic QCD and light front. I haven't worked yet on that, but I intend to do that in the next stages of my work. So let me tell you about this recent work that I've done with my PhD student, Adam da Silva Jr. We work at Rio de Janeiro Federal University, and this is very recent work. It hasn't appeared yet in arXiv. I hope it will appear very soon. First, the summary. Just a brief not very brief introduction about the motivation of why it's important holographic QCD. Then I will describe how to incorporate vector mesons in a confining holographic QCD model. Maybe this is the novelty of the work. We also will describe nucleons in confining holographic QCD. Then I will present the results for the spectrum of these guys, of these hadrons. And finally, I will tell also about a recent work that I've done with Tobias Frederico, Wayne De Paula, and Luis Mamani on this problem of spontaneous chiral symmetry breaking and confinement, and then I will conclude. So this is I'll pass very fast through these slides. It's just all of us, the people present here, want to solve this Lagrangian in the non-perturbative regime, and we love this theory, but we know that it is very hard to solve. And what we know for sure about this theory is that it is the beta function is negative, and we know how the running coupling behaves, and we know that it is small in the high energy regime that allows us to consider perturbative expansions. But on the other hand, it becomes large in the low energy regime, which means we require to implement non-perturbative methods. Just to mention the standard non-perturbative methods, the most established are lattice QCD and also the Dyson-Schwinger equations that in QCD they are also known as the Bethe-Salpeter equations. And I just cite other approaches that are important in QCD, non-perturbative QCD, chiral Lagrangians, Namujian-Arasini, light front, QCD some rules, and there's also renormalization group equations. Of course, I'm forgetting other approaches. I apologize for that. Just to motivate the holographic QCD, it must just remind the connections between the hadrons and the strings. So it started with the classification of hadrons into radial trajectories, the so-called Chu and Frocci plots, that motivated the possibility of this relation between the square mass and the spin being associated with one-dimensional objects, either open strings or closed strings. However, when people calculate the spectrum, although they obtain these nice trajectories, they also obtain one particle that is not present in QCD, which is a massless spin-2 particle, which is the graviton. So it took some time for string theories to realize that string theory necessarily implies the presence of gravity. So it's not directly applied to QCD. However, there's been some development of also some effective string theories for in 4 dimensions for mesons, but it is like a different approach. The standard string theory necessarily implies gravity. Another motivation for this connection between QCD and string theory is the Veneziano amplitude that was proposed by Veneziano to satisfy the duality TS in the scattering amplitudes, and this was realized that it comes also from considering a scattering of open strings. So there was another hint of a connection between hadron physics and string theory. But the most established connection between QCD and string theory was obtained by Toft in 1974. This is the connection in the Larsen limit. He showed that if you consider Feynman diagrams in the Larsen limit, then you can reorganize your Feynman diagrams in terms of topology. You will find that the planar, so-called planar diagrams are the ones that dominate. And he also realized that they will be similar to the diagrams that you will find in string theory. And in this scenario, you have to work with this effective coupling, which is called the Toft constant. This is just the Young-Mills coupling, G squared times the number of colors, where this guy will be keep fixed while you take the limit NC going to infinity. Then it came the ADS-CFT correspondence. Initially, perhaps the most important breakthrough in string theory in this context was done by Polchinski, that discovered the so-called D-branes that are some hyper surfaces in 10 dimensions, where you can consider boundary conditions for open strings. If you consider open strings, the endpoints can lie on those hypersurfaces. But at the same time, it was shown that these hypersurfaces are non-perturbative solutions of string theory in the closed sectors. So they can be associated with solutions of associated with closed strings. So this suggests some duality between open strings and closed strings that ended up on the ADS-CFT correspondence, which is a duality between Yang-Mills theory, which is the theory that arises from open strings, and string theory associated with closed strings. So but it was in a particular setup where you have to pay a price that is not exactly Yang-Mills. So you need supersymmetry, you need extra ingredients. Actually, one of the ingredients, important ingredient, is Larsen. You need to take the Larsen limit. And another ingredient is conformal symmetry. So that's why it is called ADS-CFT. ADS comes from the idea of a 5-dimensional anti-de Sitter space. This is like you can imagine an ADS space as some kind of box or some kind of a rigid board, so that you can define properly a boundary. That's the nice feature of ADS space, and it maps to a theory on the boundary that needs to have a conformal symmetry. So this is the ADS-CFT correspondence. But then this correspondence can be thought of some gauge gravity duality between this is a very specific setup that was Malacena that found that extremely from it is very this is so-called the top-down approach. And you can show exactly that this theory, n equal 4 superior Mills in 4 dimensions, maps to this theory to the low energy limit of this string theory that is called supergravity, type 2b supergravity. And as Enrique explained, the ADS space it's easier to describe in the Poincaré. Is the Poincaré coordinates. You have this spatial radial coordinate that is associated with scale transformations, basically, so to dilatations. That's why this is this figure, just to show how as you change the radial direction, you change your scale. And the dictionary was proposed by Gapser, Klebanov, Polyakov, and Witten. That the idea was that these fields in ADS, this box, ADS space, they should couple two operators on the boundary, those the CFT operators. And this is the dictionary, basically, to identify the partition function of the conformal field theory in the boundary with the path integral of this gravitational theory on ADS. So ADS-CFT motivated holographic QCD in two approaches. There are two approaches, the top-down and the bottom-up. The top-down starts with the original ADS-CFT correspondence, and then by deforming the original brane configuration, they try to break the supersymmetries of the original theory of n equal 4 by basically introducing some kind of mass terms for the supersymmetric partners. And that's how they end up with some QCD-like theories that would map to some deformed string theories. This is very nice. However, the backgrounds that they found, they are on one hand very complicated, and on the other hand, they are applicable only for very low energies. So you can, for example, reproduce things like the chiral Lagrangian. You can reproduce things that you expect in real QCD, but only at very low energies. If you increase a little bit the energy, then you will find a zoo of many string states that don't correspond to anything in QCD. So that's the big problem in these approaches. The other approach is the bottom-up that starts with, you forget about the string theory. I mean, you can keep some ingredients, but the idea is that you start with ADS-CFT. You imagine that you have some conformal field theory in 4 dimensions, that map to Einstein gravity in ADS 5. And then you just ask the question, what happens if I deform the conformal field theory, but a particular set of operators? You just say, what if I turn on some operators that are relevant, that those operators should break conformal symmetry, and then you ask, how can I describe this breaking of conformal symmetry? And the idea is that those operators are motivated by QCD. For example, one of them is a scalar operator that will appears in almost every holographic QCD model, that it's responsible of breaking conformal symmetry. That operator, you could think of some kind of a correspondent of the gluon condensate operator in QCD, or the Yang-Mills Lagrange. So that's one operator. That will show another operator also, that is the quark mass operator, for example, which is very important to describe chiral symmetry and so on. But that's the spirit of the bottom-up approach. You turn on operators. You start with a CFT. You turn on operators that mimic what happens in real QCD. As Enrique described, it started with Polchinski-Strassler, and then when further developments, there were the papers also by Professor Braga and Boschi, and you have also these developments by Ehrlich, Katzon, Stefanov, that describe chiral symmetry breaking. Then Katzon, Stefanov that introduced the softball model. Then Gursoy, Kiritsis, Nitti, it was a pioneer work on Einstein dilaton, holographic QCD, which also Gupser-Nelor. So these are perhaps some pioneer works on this area. Now let me start with my description of my work, my recent work. First, the idea just to tell you how can you describe confinement in Einstein dilaton. I follow the Einstein dilaton holographic QCD approach. It started with Gursoy, Kiritsis, Nitti, but in more recent works, the idea is trying to simplify this Einstein dilaton approach for confinement. And you start with this Einstein dilaton gravity in 5 dimensions. The potential, dilaton potential, should contain a constant that will associated with a cosmological constant. But if you expand it, we'll also have some massive term. So this scalar field is called the dilaton. So this will be dual of a scalar operator. The scalar operator that I mentioned that will be responsible for conformal symmetry breaking. So this is the basic setup when you have a metric and a dilaton. As I said, the dilaton maps to a scalar operator. The metric maps to the stress tensor operator, or the energy momentum tensor. So this is the basic setup. So this should correspond to the glue sector in QCD. So we are considering Larsen, the Larsen limit, where the gluons are dominant. So this setup would correspond to the physics of the glue sector, like glue balls, for example. You can actually describe the spectrum of glue balls, as Professor Braga and Boschi Filho did, using this kind of setup. Glue balls of a spin 0, of a spin 2, and so on. But I'm more interested here in just description of confinement. So in order to find solutions, so I'm looking for solutions that are consistent with these Einstein dilaton equations, right? So I start with an ansatz that basically generalize the ADS space. Now you have some kind of a scale factor or inverse scale factor. This zeta of z that generalize this is some kind of warp factor. And these are the Einstein dilaton equations, the independent ones. And some people prefer to work with the warp factor, which is related to this inverse scale. And the idea is to find solutions that are consistent with the Einstein dilaton equations. So let me remark that in the softball model, for example, you don't find the softball model is not a solution of Einstein dilaton equations. So the nice property of these models is that you find backgrounds that are solutions of Einstein dilaton equations. And it was found by Katzon, Stefanov, and Gursoy-Kirisis-Nitti, that you really need this property, that the dilaton has to be quadratic, far from the boundary, at a large set in the radial direction, in order to have linear confinement. I mean, confinement and a linear spectrum. And inspired by this, I consider these simple analytical models that satisfy this property. This is what I call model 1 and model 2. Just analytical solutions of Einstein dilaton that satisfy this property. And in fact, if I calculate I investigate the confinement criterion, what was found by Kinard, Stryver, and Sonnenschein. Basically, you take this function, and this function has to, they found some kind of theorem for this kind of backgrounds, this class of backgrounds, that this function needs to have a minimum at some point that has to be different from zero, greater than 0. And in fact, for these solutions that I've presented, you find always that this function possesses a minimum that is different from 0. That minimum is associated with the string tension of the Cornell potential. So you can actually prove that these models lead to a Cornell potential, quark-antiquark potential that is linear. Okay, now about vector mesons. Sorry, how much time do I have?
10 minutes.
10 minutes. All right. So about vector mesons. So the idea is to now to incorporate vector mesons. The question is what is the current that is responsible for vector mesons? What is the operator? Is this a flavor current? And this flavor current you can describe also in terms of right and left currents. And in holographic QCD, what you do is to map these currents into gauge fields, non-abelian gauge fields, left and right. And then you expand these fields into perturbations, and you can truncate at second order just to find this. And I'll focus on the vectorial sector in order to describe what I want to describe is the spectrum of vector mesons. So you just need to truncate at second order. And if you do that, I forgot to say that the coupling of this Yang-Mills sector you can fix in the end by comparing to the current correlator. I show you how it will be the current correlator. It is fixed by ANC counting rules. Okay, so when you consider this action, this is the action for the vectorial sector. This is like some kind of you can think of some kind of set of Maxwell actions, but yeah, let me remark that it is minimally coupled to the dilaton. You have exponential of -5. Right, so this is important. This coupling, minimal coupling to the dilaton, and then when you vary this action, you get the equations of motion, and you get a boundary term, a surface term as well. Then, by analyzing the equations of motion, you can first decompose your field, 5-dimensional field, into the component along the radial direction and along the transverse direction, and then the transverse direction you can also decompose into a pure spin 1 field, this transverse field, and a longitudinal part that would correspond to a spin 0 field. Since the spin 0 field is not physical in this context, you can actually prove that the consistent solution for the longitudinal part is 0. And you can set also by gauge symmetry. You can use gauge symmetry to set the set component to 0. So in that way, you end up with only one equation for this spin 1 sector, and then you can take an ansatz for this to rewrite this equation into a Schrödinger form. This eta mu is the polarization of this vector field, and this is some kind of Bogoliubov term that allows you to write this equation in a Schrödinger form. And so this is convenient for solving for finding the spectrum of vector mesons. And now let me talk about the VEF, the expectation value, vacuum expectation value of current operator. Basically, what you do is to get the on-shell action, or it could be even off-shell. You can take the off-shell variation of the action with respect to the source, and you get a conjugate momentum, and then you evaluate on-shell. This should be equivalent to taking the on-shell action in the end. So this is the dictionary for the expectation value. This is the holographic dictionary for the VEF of this current operator. And we can also define the bulk to boundary propagator is that relates the field in 5 dimensions to the source in 4 dimensions. So this is the bulk to boundary operator. And this is useful in order to rewrite the on-shell action in terms of the sources, and then to identify the correlator, the current correlator. Basically, the current correlator will be associated with this guy, with this kernel. So this is the holographic visionary that you get for the current correlator in terms of this bulk to boundary propagator. And it's consistent with linear response theory. Sorry. Okay. Okay, then you take this transverse, the tensorial part, I mean the Lorentz part, you can write as because it is transverse in this way, and then you just get only a scalar function for this bulk to boundary propagator. This is a simple answer that guarantees the transversality of this guy. And then you find this equation for this bulk to boundary propagator that it's interesting to rewrite in this Sturm-Liouville form. If you rewrite in the Sturm-Liouville form, you can, of course, apply a Sturm-Liouville theory in the sense that you will introduce a Green's function, and this Green's function will admit an spectral decomposition. That's what we do. If we consider a spectral decomposition of this Green's function in terms of the so-called Sturm-Liouville modes, which in ADS-CFT or in holographic QCD will correspond to the normalizable modes. These are the normalizable modes that satisfy some normalization condition, and this equation for this sector. And you can find a relation between the bulk to boundary propagator and this Green's function. And in that way, you end up with a spectral decomposition for the current correlator. So this is the current correlator, and this is the spectral decomposition for the current correlator. And this decomposition is what you expect in large QCD. So this is a nice result. So for nucleons, I forgot to mention that in vector mesons, there were some pioneer works by Grigoryan and Raduskin, and also Erlis Katson-Stefanov and Kars Katson-Stefanov. And for nucleons, the pioneer works were Brodsky-Teramont, Hong-Inami-Yi, and then Abidin Carson. So for nucleons, what you want is to incorporate a nucleon operator. We consider this Joffe operator, and this Joffe operator we map to a Dirac field in 5 dimensions. So we start with this Dirac action, and this Dirac action we have some covariant derivatives, some spin connection, field bands, and so on. And it turns out that for this Dirac field, it doesn't matter if you have exponential of -5. This coupling you can actually is not physical in the sense that you can always rewrite your spinors in such a way that that coupling disappears. That's why it was a little bit difficult to describe nucleons in holographic QCD, because this minimal coupling is not enough. You need something else. So the new ingredient that you need to describe nucleons is this 5-dimensional mass. So basically what you need is to incorporate some kind of running mass, some kind of coupling here of the dilaton and the metric, so that you end up with some kind of a harmonic oscillator potential. I'll show you details. So this is just some technical details about the field bind, the spin connection, but in the end, you end up with this effective action. This is in 5 dimensions. You end up have some kind of Dirac equations for psi and psi bar. And you end up. So this is the action. If you vary the action, you find the Dirac equations in this curved background. You find a boundary term as well. And it turns out that the boundary term it has to be corrected, right? And you can see that when you decompose this spinor into right and left sectors. When you decompose into right and left sectors, then you will find that the right and left sectors are coupled, And it means that this surface term is not correct. It has to be corrected because these two terms cannot be independently fixed. So you need to add this correction so that you end up with a correct variational principle. So if you do that, you can actually fix one of the sources, and we choose to fix the left sector. Okay. So let me just skip this part. Just let me tell you that you can play the same game and end up with a spectral decomposition for the nucleon correlator. This I just mentioned this was our proposal for the running mass. So this is the spectral decomposition that we find for the nucleon correlator. And then let me just show you quickly the numerical results. So for this vector meson spectrum, we find results that somehow improve the soft wall and hard wall models, that in the sense that get closer to experimental results. And now let me show you for nucleons. Also, we find two scenarios, two interesting scenarios according to the conformal dimension, and that also improve, at least for the high excited states, it improves the comparison to experimental data compared with previous approaches like soft wall and hard wall. So these are the main results. The K constants also we managed to calculate. We have few places to compare, but we intend to look for some other works, or even theoretical works to see how we do. So that's it. Let me just mention that recently I worked with Tobias Federico, Luis Mamani, and Wayne DePaula on incorporating spontaneous chiral symmetry breaking, and we have managed to find a nice chiral condensate that evolves dynamically with the quark mass. And for more details, you can see this paper. So that's it. So conclusion. So thank you.
Thank you, Alfonso. Right now it's time for questions. Question? Okay, now I have a simple question. So is it possible to extend your method to, let's say, other method other than vector method, like a scalar or maybe tensor method? Is it possible?
Yes, it's possible. Actually, in this work with the Tobias, Professor Tobias, and Wayne DePaula and Luis Mamani, we have incorporated scalar mesons. We have scalar mesons. We have pseudoscalar mesons. The scalar mesons and pseudoscalar mesons comes from this field, this X.
Wow. So
this X field will contain the pseudoscalar once you perturb. It is a complex field that you can perturb. You have some part associated with the modulus and some part associated with the phase. Part associated with the modulus is a scalar, and the phase is the pseudoscalar. And you can also describe from these guys, you can describe also the axial mesons. And it's also possible to extend to higher spin mesons as well.
Okay, thank you. If no further question, we can start the coffee break, right? Coffee break now. Okay. So when, yeah, thank you again. So when should we be back? 30 minutes. Yeah, 30 minutes. Yeah. Joel Pacheco de Mello. He will talk about exploring the covariant form factor for spin 1 particles.
Thank you, Jimbo. Thank you, pronunciation is correctly. I'm very pleasure to be here. And thank you, organizer, for this invitation. Very pleasure. I am in CBPF, one of the most important institutions in theoretical and physics. In physics, no, also experimental. That's the house of Leite Lopes, Mário Schember, and Cesar Latz. That's a very pleasure I'm here. I don't know, this thing not work with me. Why? Okay. I explore the covariant form factors for spin 1 particles and in equal time, and also in light front field theory. Then I give some overview about light front motivations, overview light front spin. I say something about spin 1 particles. I define my electromagnetic current, show results and some conclusions. Then motivation. Light front is ideal framework to try describe bond stage, because it's natural language, for example, for deep inelastic Compton scattering and so on. Also to calculate Bethe-Salpeter amplitudes, bond states, and you have an unambiguous particle content of the hadronic system. Then the wave function in light front is really the representation of composite systems in quantum field theory. And another advantage is the invariant underboost. Light front almost is vacuum, is trivial. You see the talk by Lubo, but Bandovinic. After integrating K- energy in light front, you can obtain the wave function from the Bethe-Salpeter amplitude. The Lorentz Hamiltonian is the Hamiltonian in light front is Lorentz invariant. Okay, I give a little bit about light front. I use the usual x plus is x0 plus x3, x minus is x0 minus x3, that is position, that is time. My metric tensor is usual. Someone not have a square root 2 here, depending what you use for the metric. I use this one for the quadri-momentum scalar product. Then you can relate P plus quadri-momentum with P0 plus P3, P minus P0 minus P3, P pair P1 and P2. Then the quadri-momentum product is given for this, and the P plus P minus in quadri-momentum. Then Dirac matriz plus is gamma 0 plus gamma 3 is G plus component of the current. Gamma minus is gamma 0 minus gamma 3, is the G minus, and G pair gamma 1 and gamma 2. And because the metric, the light front dispersion relation is more simple to equal time. It's linear. You see P minus is energy, is linear, is different from the equal time. And on-shell boson is a propagator, Feynman propagator is the same. But fermion, you have this guy here. This guy is more or less complicated. That is coming to 0 modes, non-valence. It's a nice, quite nice reporters for young people. Very nice for Brodsky, Paul Lipinski, Professor Brodsky, Arindana, on Indian Journal, and also a book for Professor James Very some years ago. But it's very nice book, many very interesting papers there. Then I defined my electromagnetic current for the component plus and minus under the gamma prime and gamma polarization, final and initial polarization. That you have, it is a very nice reference for Franz Gauss and Schumann, Journal of Physics G, but if for deuteron in reality. But you see, I speak about the Rho-Meson scale, but that is the same for deuteron because it's P1. Then I have these 3 form factors, F1, F2, F3. That's the most simple way to describe spin 1 particles. Deuteron also have spin 1. Okay, that is my main equation to calculate the current. Then my kinematics, bright frame is my initial state, quadri-momentum. My final state, quadri-momentum. I have direction, only axis direction. And the momentum transfer is Q mu is 0, Q mu only x direction, 0, 0. Then my polarization in Cartesian base, eta is the square for the momentum transfer divided 4 times rho meson square, okay? That is my polarization I use to calculate these matrix elements of the current. Then after calculate for the plus component, I obtain, in terms of the matrix element of the current, I obtain F1, F2, F3. And I obtain polarization X hash, IA, ZZ, ZX, GS is just because you change the final with the initial, then you just change here the signal is the same, you see? Then this, you have 9 matrix elements, but 4 gives 0. Then you have only 5 here. You see, it is another one gives 0 because my choice of polarization, okay? Okay. Then you can invert these matrix elements, you obtain with the plus component of the current, you obtain F1, F2, now I'll call plus in this way, no? It's combination of the matrix elements J, no? F1, F2, F3, okay? Now I obtain also the minus component. If you see the expression is quite the same for minus component. Also, another one gives 0. Still, I have 5. And I obtain F1, F2, F3. I'll call minus now because I calculate with the minus component. Okay? Still the correct here. So the change of signal because I change the final polarization with the initial polarization. And now I go to spherical basis. It's like it is way. It's very technical. Not worry about that. Then they obtain Cartesian spin basis the matrix elements for the current for minus component, for plus component, minus component. Then I use Melos rotation, it's quite technical, so to connect the matrix element light front like this with the previous one. Then you just made a Melos rotation. Then you obtain the matrix elements in the terms of the previous basis, the light front basis here. You see? 1, 1, 1, 1, 0, 1 minus 1, 1, 0, 0. Another gives 0. Then you have 4 matrix elements for light front. Also for minus component is the same. The form of the expressions is the same. It's very funny. And now in this preliminary work, I not use the complete vertex for spin 1. For Rho meson scale, I use just gamma mu. Then I use the gamma mu plus and minus here, just to show something. I need to complete this work with the complete vertex, but it's just a start. Then I need to calculate this time amplitude here, okay, the trace and so on. But this amplitude is divergent. Then I need to put like Paulo Villares, some regulator. I use this because after integrating K minus, I obtain like the Betz-Salpeter amplitude wave function on the light front. Now in light front, you have something found by Inagati and Kondratyuk many years ago, in 84, 89, one thing she called angular conditions. If the rotation symmetry as respect AA, ZZ is 0 in equal time. That is in light front and equal time. In equal time, it's true for plus or for minus. This delta is called angular condition. Is okay, next slide. Okay, but for parity and rotation, that is true in equal time. Okay, quantization. But it's not true in light front. It's not true. It's a long time ago, you know, Professor Gierman, people here, you know, it's not true. But if you form factors, covariant, are really covariant form factors, F1 plus is equal F1 minus. And you can plug in the angular condition minus or menos elements of the current, that you obtain immediately 0, 0, okay? That is prove the angular condition coming 0, no way. Okay, what is happening? What is happening, you need to restore its covariance, you need this no valence component or zero mode. People discuss a lot here. You have the valence component in the triangle diagram, and you need add this guy here, okay? That is, you can see the talks by Wayne Polizu, Professor Wayne, Lubo, James Berry, Chandal, also Professor G. Sorry, I sent before your talk. Yeah, okay. And I have a work many years ago. I developed some dislocation pole method. You have an amplitude finder. You dislocate which pole you want. You dislocate the pole. In the end of the day, you put the momentum transfer plus goes to zero. Then you recover the covariance. You take the minus component plus the zero modes. That is in some work in 98, also 98 on field board system, nuclear physics. Also Professor Chang, Yang, Salvik, also a long time ago, think about this. Okay, now what is the problem with covariant spin light front spin 1? Because you have only 3 form factors, charge, magnetic, and pole. But you have 4 elements of current from the angular condition. You can combine every way you want. Then you have the most famous prescriptions, Frederick Frankfurt Stickman, Ina Grashka Tayaku, Koster, Chung, Keister, Polizu, Brotz Hiller, Professor Kamanov. No, it is in this work, more details if you want. And Ina Grash eliminate the component 0, 0 plus. She not eliminate minus because she not calculate minus. I am that calculate. Then they have this combination. Is that important? You see, 0, 0 is not here. Polarization 0, 0 is not here. For these 3 form factors, it's not here. Then you have the Koster-Keister Polizu prescription. He used the 4 matrix elements in light front, writing Cartesian basis like this. Okay, that is important. That is in this paper. Then you have the Brotz-Hiller combination. Eliminate 1, 1, and use another 1. Okay, that's another prescription in this paper 9.2. And Frederick Frankfurt Stickman have another combination for charge form factor, and you use for magnet the same Koster-Keister Polizu, Pole also. That is in this paper 9.3. And Professor Kamanov use another prescription. You see, he eliminate 1 minus 1. Okay, in this paper. Then I found some years ago, 3 or 4 years ago, in the terms of direct trace, the 0 mode for AA is 0, for GG x-axis 0 modes is proportional to ZZ, Z-axis is proportional to ZZ. You see, eta is, remember, is the momentum transfer squared divided 4 times the whole meson. Then I have this relation. This is 0 mode is related to valence component of this polarization minus valence component of ZZ. Okay? And after work a little bit, you have this nice relation between the all matrix elements. And then you can use all this to eliminate 0 mode in level of direct trace. Then you go to light front matrix elements. Then this 0 modes 1, 1 gives 0, 1, 0 also gives 0, 1 minus 1, 0 mode gives 0. Only 0, 0, 0, 0 is not 0. That you remember, Ina Grash eliminate exactly this by chance, I don't know, by feeling. She eliminates exactly the term give problems, the term broken the symmetry. She eliminates. Does not have any 0 mode in the prescription by Ina Grash. There are some papers with similar work by Professor Shang-Ji, Ben Barker, and Choi. It is 2 publications in physical heavy G. Okay, now I prove. I use my relations, plug in the Ina Grash prescription, and obtain 0. It's not numerical calculation, it's exactly. It's not numerical calculation. Zero mode is inner gauge prescription is free of zero modes. That is proven to two physics letters B by myself and Tobias Federico. Okay, then inner gauge is completely. I'm not sure there are another prescription, but you can follow in these papers. You see some broken a lot. Okay, I just proved the inner gauge because this preliminary work I use just then my F1 covariant. I use this 0.43 for quark mass, constraint quark mass, PDG mass of the whole meson, regulator mass. That's two masses is fixed by the K constant from the particle data group. If you see the with G plus covariant, G minus red, and green because I use AA, not have any zero mode. Is give the three curves that give the same result. That the minus component blue, then the broken the symmetry, you see? It's completely different. It's broken a lot. Oh, sorry. After I add zero mode, all curves give the same, you see? Up to 10 GV square. Now, F2 also, you see the black, red, and green give all, and green also broken the symmetry, you see? If plus component, F2. You see, but with covariant calculation, equal time, plus and minus give exactly the same result. Blue is here. After I add zero mode for plus component and minus component, I obtain recovery the covariance here, up to 10 GV. I can go more. And F3 also the same thing, broken a lot, the covariance. These three curves, black, red, and green is here. Green also broken, sorry. Then after a blue here, minus. After I add the zero modes component, like I showed you before with that relations, I obtain exactly the same result. Also, the is a angular condition. See, zero in equal time for minus and plus. But in light front minus, if I have only valence component, that's the plus component of the angular condition, no? Is broken. After I add, is the green line here. Is the black, the green is the same. Sorry. It's the plus component. Now, minus component, broken a lot. Is the covariant calculation, the light front calculation. After add no valence plus no valence, zero modes, I obtain exactly the same. What I have done. Okay. Fine. Yeah. And now the form factor G charge, no? And the covariant is black, is here, impossible to distinguish because with minus and plus covariant, I use inner gauge prescription, but it's no matter which prescription I use. If I calculate covariant, no matter Custer, Polizu, Bosca, Hiller, Federico, Frankfurt, Stickman, no matter which prescription I use, no broken of symmetry. But if I use light front coordinates, light front conjugation, then I have the broken. You see with G minus is a red, complete, no, different. After add, you have light front plus no valence. Then I have the, it's impossible to distinguish, okay? And G1, magnetic form factor, the same. You see, there's a light front minus. After add, every curves is here. For covariant with J minus, J plus, J minus, and light front with J minus. Because not have zero mode for the form factor. Because I use the inner gauge prescription. If I use another's, you have the zero modes. If you go to reference, you see, okay? Maybe I not show on curve here. Maybe. And for the G2 quadrupole form factors is the same. You see, after add zero mode or covariant calculation, give the same. G minus is here, broken. a lot. Another thing interesting for the charge, because this form factor, like deuterium, have a zero here. It's about 3 GeV squared. This zero depends Schrödinger dice. People found about 5 GeV, because it's 6 times for this calculation. Schrödinger dice on K-Hopkins and another one is 6 times the square root of the whole meson. Then he found about 5. I found about 3. Another people in literature also found this zero about 3, because the charge form factor change signal. Okay. I don't know, am I here? No, I think I speak here. Okay, I think I almost finished. Okay, light front, you can use correctly, describe hadron bond state. That is good. Take new information about new bond states, heavy mass and so on. But you need care about breaking of rotational symmetry. You have to be evaluated. The inclusion of zero modes or part terms is crucial. The break of rotational symmetry for G minus component of the current is very pronounced. You can see that with the inclusion of part term, you have the covariance restored. Next, this work is obvious. Put spin 1 full vertex, and maybe Newton or Carl star, and so on. Thanks so much for your attention.
Thank you, Pacheco. So now it's time for questions.
Does this mean you can actually calculate the two-body parts of the current you actually need to restore covariance in the light front?
I think so. I think so.
Very nice.
You know, depend of you have the numerator, your amplitude, K minus. If you have K minus, you need K very careful in numerator. Okay, if you have K minus. For the pion, gamma plus the current, the zero mode is cancelled out. For the pion with the Del frame.
Okay.
Maybe I just to make one comment.
Why?
You know,
Sure.
you mentioned about the spin 1 as a deuteron or the rho
Yeah.
meson, that kind of bound state. But the thing that you talk about actually works also the elementary particle,
Oh, yeah.
like a W plus.
Yeah.
And then you just use a standard model.
Yeah.
Then you can actually see that this zero mode in the good current
Yeah.
has this zero mode that at least the 0 to 0 part.
Yeah.
So all the things that
No.
you're talking also work in the elementary particle.
I think you have a paper about that, no? With Ben Babaker, I know. Thank you, Mr. G.
Any further questions for Pacheco? Okay, I have a question. So, the technique you presented, does it depend on the wave function, or basically it works for any wave function to recover the covariance?
That is very deep, is in the level of direct trace. Yeah, I don't know, you I am correct, you think about this thing, no? You talk about this thing, no? It is a level of direct trace. It's not depend of any model.
Okay.
It's a level of direct trace.
Okay.
The trace direct you found this thing, this calculation. You have only 0 give contribution. Another guy is not have any contribution.
Okay, so
That
basically,
Inagat have the feeling. She eliminated just the correct one. If you go to another prescription, or I think before, people use, sorry, Jimbo. If you go to another, you see, Brodsky, for example, Professor Brodsky, eliminate 1, but Inagati eliminate Inagati. She eliminated 0. You not have 0 mode here. No matter your model you use.
okay. So basically using this
Yeah.
prescription, one can always get the same results as a covariant.
Exactly. If
Okay.
you use this prescription, you obtain exactly the same result.
Okay. Any further questions for Pacheco? No, another question. So,
Please.
if let's say we calculate the particle for even higher spin, like spin 2, is there
Spin
any
2?
yeah, spin 2 as
Oh,
straightforward?
I never
way
looked,
to-
but I think a good job to thinking.
So this is a method that is not naive, cannot be naively, let's straightforwardly, let's say,
No, I can try.
extend to
I never
higher spin.
calculate, but I can try.
Okay.
Okay, maybe spin 2. I don't know, Professor G. You have the idea for spin 2? Gravitation from far. That's right. Maybe, yeah, sure.
Okay.
I can calculate also, yeah, sure. Gravitation.
Okay.
Sure,
So-
graviton. Sorry. Yeah, exactly.
Okay, so if no further questions, let's move to next speaker.
Thank you.
So next speaker is Satvia Kao. She will talk about structure of spin 1 QCD systems using light from Hamiltonian approach. Yeah, go ahead, please.
Good evening, everyone. First of all, I would like to thank the organizers to provide me the opportunity for talking into this prestigious platform. So I will be talking about the structure of spin 1 QCD systems using light front Hamiltonian approach. Particularly, I will talk about the rho meson structure. This work has been done with the collaboration from IMP, people from IMP, and with Professor James P. Very from Iowa State University. Okay, so first of all, I would say why we want to study this rho meson structure. And then I will briefly go through the BLFQ approach in which we have done all the calculations. And then I will move towards the transverse momentum distributions of the rho mesons, which are, I mean, it gives the structure of rho meson in the momentum space. I will talk about both the quark TMDs and gluon TMDs. We have studied a few gluon TMDs, not all of them yet. And then I will explain the PDFs that we have studies of the rho meson, which are the integrated version of the TMDs. And then I will conclude my talk. Okay, so our motivation behind this studying this rho meson is like, as we know, the rho meson carries the nuclear force within the atomic nucleus, so it's crucial to study this particle. And the second thing is we want to understand the splitting between pi and rho meson. So yeah, so this is like we all know that pi and rho have the similar quark component, but they have huge mass difference between them. So it is very interesting to understand this. And then spin 1 has a special structure, that is a tensor structure that comes from this tensor structure functions. So that cannot be found in spin 0 or spin half systems. Although there is no experimental data available for this rho meson structure functions, but there are some latest data available for this gravitational form factors and the moments of PDFs. Being a spin 1 particle, deuteron also has this tensor polarized structure, and it has some experimental data by Hermes. But a few data points are there, so many experimental data, experiments have been approved to study this special structure function, like JLab proposal has been approved, and Fermilab, and many more. So they're going to study this structure function, and this is still a largely unexplored field, but yeah, it can open a new field in spin physics. Okay, so we are interested in studying the quark and the parton dynamics in the hadrons in momentum space. So we would like to study this transverse momentum distribution functions. So these distribution functions provide information on the transverse parton dynamics and are convoluted in the cross sections of the CDs and Drellian processes. And they provide the three-dimensional structure functions as a function of longitudinal momentum fraction and the quark transverse momentum. Also, they are interesting to study because they provide the information on the spin and orbital angular momentum of the partons inside the hadron. Okay, these are a few publications which holds the data, holds calculations for model calculations for this rho meson study or spin one study of spin one targets in the momentum space. And yeah, and there are some formalisms, basic formalisms on this spin one structure. So first of all, we want to study this quark TMDs in the spin one system. There are total 18 valence quark TMDs. 9 of them are T even and 9 of them are T odd. The blue ones are T even, and yeah, the red ones basically are the T odd functions. They also have these. This spin one system has this special distributions, which are the tensor distributions, and cannot be seen for the spin one Celestian spin one systems. So yeah, so this is interesting to study. Then we have Gluon TMDs. There are total 13 T even Gluon TMDs, but yet we have not studied all of them. We have only studied this F1G1, F1LL, yeah, and this H1TT. So yeah, now we have all the distribution, we know all the distributions. Now we need the formalism, the framework to study these distributions. So we chose the light front framework to study this. Now we just need the light front wave functions, which can provide the, once we have light front wave functions, that can provide the 3D imaging of the hadron and the information on the spin. So there are this general distribution, the Wigner distribution that can be that can provide the transverse momentum distribution and generalized parton distributions when integrated out this on some limits, and further integrating out them on some limits that can provide some parton distribution functions, which are the one-dimensional distribution functions. Yeah, we will also study this. Then yeah, okay. So now we chose this basis light front quantization approach to study these observables. So this is many people have been talked about this from the day, since the day one, they have been talking about this basis light front quantization. So yeah, this approach is a non-perturbative approach based on this Hamiltonian formalism. Yeah, we are solving this eigenvalue problem to solve this relativistic many-body bound state system, and it facilitates us with this mass spectrum and light front wave functions. So we have successfully been, this approach has been successfully implemented on this to study this spin 0 and spin half systems. Now we want to extend this approach to study the spin 1 system. Yeah, so this Hamiltonian light front Hamiltonian is a combination of this light front QCD Hamiltonian plus the confinement. Then we have taken right now for the meson systems, we have taken up to this Fock sector, the second Fock sector truncation. And yeah, each Fock sector, each particle in the Fock sector is defined through this basis functions, and in the transverse direction we are taking this two-dimensional harmonic basis, and in the longitudinal direction we are taking this plane wave. And now to truncate this infinite, to limit this basis and the Fock space, we need truncations, and in the Fock space truncation we are just considering up to this, as I have already told. And the basis truncation, we have this two basis truncation parameters, this in the transverse direction and this is in the longitudinal direction, the K. Okay, so for the light front Hamiltonian, we have the three terms, light front, yeah, the kinetic energy term of the quarks and gluons, then the quark-gluon vertex interaction, and the instantaneous gluon interaction terms. And other interactions are absorbed in some parameters introduced in this formula, in this approach. And the confining interaction term is like this. This is in the transverse direction and the longitudinal direction. This is adopted from light front holography. This is some phenomenological modeling. Okay. Okay, so yeah, this is again the same. We are taking this mathematically, we are taking these two interactions into account. Okay, yes. Now, yeah. So this term is 0 yet, but when we include the higher Fock sectors, this term will be non-zero. Okay, now to set the parameters, we fix some pi and the low-lying states to fix these parameters, and then we will study the structure of the various various mesons. And yeah, so we found that the probability of pi in the leading Fock sector is like 0.49, and the higher Fock sector dominates over it. And the decay constant for the rho meson, we found that it's a little bit low against the experimental data. Experimental data is about 220 MeV, and it's quite, yeah. Okay, so this mass difference between this pi and rho, we found that it is coming from this MF, that is the phenomenological mass parameter in the vertex, in the vertex interaction term. So the gluon is playing a crucial role in here. So yeah, we have kept all the parameters same, and just change this MF value and said it that this difference is coming from MF. Okay, so the contribution of different components, wave components of the light front wave functions in these pi and rho mesons are like this. We have found that the S wave dominates over other waves, and yeah, for both the pi and for the rho meson. For the pi, we have like two spin projections like 0 and ±1, and for pi, yeah, we always found that the higher Fock sector dominates, but our P wave is like very weak, and D wave seems like extremely weak. So now we want to observe them on the level of the distributions. So we found that for the pi and rho meson, we want to study that, compare them on the observable level. So we found that these are the comparison. This solid line is for rho meson and the dashed line is for pi, and they both have this unique feature, this peak structure that has never been found in other models. This is coming from that MF, that is the phenomenological mass parameter in vertex interaction term. Okay, so now since pi has only one TMD, that is F1, so we have compared only that. Now we have studied other distributions of the quark TMDs. This one is the unpolarized, that is in the unpolarized quark distribution in the unpolarized meson, and the longitudinally polarized, this is in the longitudinally polarized meson, and this is the transversely polarized quark and transversely polarized rho meson. So yeah, except this low X region that is interesting, people have never found this kind of structure because they have not taken the higher Fock sector explicitly gluon into account. So they have never found this kind of structure. Then these distributions have the PDF limit. And yeah, we have found that beyond this X.2, they are consistent with the other model predictions. And these distributions are like, they have no interference terms between the wave compositions. These are some other distributions, Wormgear 2, Wormgear 1, and the Prestologicity distribution. And they do not have this PDF limit, and they have the interference between different wave composition like SP wave, PD wave. This is the overlap of S and P waves, and this is the SD waves. Their magnitude is very low because our P wave and D waves are very weak. These are the special distributions which can only be found for spin 1, F1LL, F1LT, and F1TT. F1TLL has the PDF limit, and it has been measured, not TMD, but the PDF has been measured for the deuteron by Hermes. And yeah, we also found that these distributions are consistent with the other modeled results, except the low X region. Then we have this GLON TMDs. We have also compared the GLON TMDs results of pion and rho mesons. Yeah, these are almost same, just the difference is in the magnitude. They are almost same in K and with respect to X. The solid line is for rho, and the dashed line are for pion. Okay, then other GLON distribution TMDs we have studied the helicity and tensor. And yeah, we have found that these distributions have kind of similar structure like the spin half system. And we found that the transverse GLON TMD is 0 in our case because of the extremely weak D wave component of the light front wave function in our case. So this can be non-zero if we consider the further Fock sectors and we include more interaction terms. And by integrating this over X and K per, we have found that the valence quark contribution to the spin is like 54%, and the GLON spin contribution is like around 50. Now we integrated these distributions out over K per, and we found that there are some pattern distribution functions. For quark there are 4, and for GLON there are 4 as well. But we cannot find this H1TT because of the weak D wave, as I said. But this distribution is also special because it cannot be studied for spin 1, less than spin 1 targets. So our calculations satisfied these both sum rules. And again, we have compared this pion and rho PDF F1 at the higher scale. These are almost kind of same, but at the end point, this rho meson distribution is falling rapidly. Okay, then we have studied these. The quark, the X multiplied PDFs of the quarks, and for the GLONs. This F1LL is found to be opposite for both the cases. It's exactly opposite. And then these are the PDFs at the higher scale. We have evolved them using the Diglap equations to the scale like 5.76. And yeah, this black one is F1, and this pink one is GLON, and yeah. Okay, then we have also compared the moments of PDFs with the available theoretical data with the Bethe-Salpeter equation and the lattice data. We found that our numbers are somewhat underestimated for this moments for F1 as well as for G1L. Yes, so yeah, but while comparing with the pion, these are almost same. for both the particles. And note that this lattice data is quite old. It's from 1997. So now the conclusion. We have studied the structure of this rho meson through these TMDs and PDFs using this light front Hamiltonian approach, along with this ordinary TMDs that exist for spin half systems as well. We have studied the tensor polarized structure that can provide the exotic hadron structure. Then we have found the qualitative consistency with other model results, except some low exclusion. And then we have investigated these clone TMDs for the rho meson. And we found that H1TT is 0, but inclusion of the more interactions can make it non-zero. And our future plans are to include multiple gluons and C quarks, and this work is in progress. Thank you.
Thank you, Satavir. Okay, now it's time for questions.
The slide 14, you have a lot of, you have some parameters. You like to know why fix these parameters, please?
So you want to know how we fix these parameters? We have just fixed these states, like these blue dashed lines. We have fixed these low-lying states, and yeah, we looked into these states and fixed these parameters. Yes, on the spectrum.
Okay, any further questions? So if no further questions, let's move to next speaker. Thank you. Our next speaker is Cheryl Hancock de Souza. She will talk about exclusive production of excited light vector mesons with a holographic wave function model. Okay, you can start.
Okay. Okay. So thank you very much, the organizers, for the opportunity for me showing my work. So today I'm going to talk about a work that I did in collaboration with Emmanuel, Roman, and Raimon, that talks about the exclusive photoproduction of light vector mesons with a holographic function, wave function model. More specifically, I will talk about the production of vector mesons in nuclear targets and why it's good to study this kind of process. Because the light mass, the small mass of the light vector mesons have a small scale that makes a lot of non-perturbative effects emerge in the process. So there's a big difficulty to describe this kind of process, mostly in the vector meson wave function. And also because there is some recent data for the whole photoproduction in lead-lead collisions. So the observable that we're interested in is the cross-section of the nucleus cross-section. But first of all, I will explain what is a coherent production. A coherent production is when the nucleus target remains intact after the collision. So we can separate the nucleus cross-section into a part that will consider the flux of photons that come from the projectile nucleus and the part of the cross-section of the photon nucleus scattering. And this factorization is good for ultra-peripheral collisions. That are the ones that have the impact parameter higher than 2 times the nucleus radius. This means that when the two nucleus they collide, they don't collide exactly one in front of the other. They are just experience electromagnetic collisions, not strong ones. So for that part of the interaction, the part of the photon flux, we will use this expression for the photon flux for the impact parameter, and the being dependent photon flux will be calculated with the Weizsäcker-Williams method for a punctual charge. And this part of the expression, the exponential one, we will exclude the part of the strong interactions between the two nuclei. And the thickness function that appears in the exponential inside the expression will be the longitudinal integration of the nuclear density inside the nucleus. And we will use the Wood-Saxon distribution for describe this distribution. This will be used here on the photon flux and after on the cross section for the gamma-A collision. And how we're gonna describe the gamma-A collision? We're gonna use the dipole model. So the dipole model, it's based on the fact that the lifetime of the QQ bar pair will be bigger than the time of the interaction of the QQ bar pair with the target. So with this consideration, we can separate the process into 3 steps. First, the photon will split into a QQ bar pair that will be the color dipole. Then this color dipole will interact strongly with the target. And after that, it will recombine into the vector meson that we are interested in. So the amplitude of this process will be the product of the amplitude of each subprocess. So I will explain each of these parts now, starting by the photon splitting into the QQ bar pair. This part, that is the photon wave function, is calculated by QED perturbatively and is very known in the literature. This part here is the vector meson wave function. Since we are interested in a bound state, a lot of non-perturbative effects will have a contribution in this part of the calculation. So we can't use just perturbative methods. We need to use a more real way to calculate this. And in this work, we use the Brodsky mode approach that is used the ADS-QCD holographic model. So basically, it considers that the scalar part of the wave function can be factorized into a part that depends on the orbital angular momentum, a part that depends on the photon fraction of momentum carried by the quark, that is the beta, and the phi is the part that considers the dynamics of the interaction. With this, we can use an effective confinement potential and solve a Schrödinger-like equation to obtain wave functions that have the shape of the harmonic oscillator wave functions. And we find these eigenvalues that will be the vector meson mass squared. The original work used a kappa that's fixed for all vector mesons, but we let the kappa depends on the vector meson mass for the ground state. So our kappa will be different for each vector meson family. So we will have a kappa for the Rho, a kappa for the omega, and a kappa for the phi vector meson. This enables us to find a good description of the spectroscopy. We're not interested in describing spectroscopy data here in this project, but we checked that our results can describe this data too, but it's just a check. And here we have the scalar part of the wave functions for the whole oneness and H2S vector mesons. As we were expecting, the ground state don't have any node, but the excited state have one node right here. It's very important because it can checks. With this, you can see the contributions of different parts of the wave function into the amplitude calculation. And after that, we have the dipole nucleus cross-section that will be responsible for describing the interaction of the dipole with the nucleus. This part of the calculation will be evaluated with the Glauber model that makes a resummation of all the possible scatterings of the dipole with each nucleon inside the nucleus. And each of these interactions is described by the dipole cross-section, that is this sigma QQ bar here. In this work, we use the GBW model for describe this dipole cross-section. And with all these considerations, the total cross-section for the gamma A process will be given by this expression here, where we have the vector meson wave function, the photo wave function, and here is the amplitude calculated with the Glauber-Gribov model. Besides that, we also included corrections, one for describe the real part of the amplitude. So we include this factor here in the sigma QQ bar cross section, and one for consider that the gluons exchanged between the dipole and the target can have different momentum fractions. So we multiply the dipole cross section by this factor here to include the skewness factor. All this expression is calculated considering that the lifetime of the QQ bar is very long, much bigger than the nucleus radius. This is a good approximation for the first state, that is the QQ bar pair. But when we consider higher states with gluon emission, like QQ bar G or QQ bar 2G, we have to consider that these states survive less time than the QQ bar 1. So maybe these states doesn't survive a time enough to pass through the nucleus. Its coherence length can be smaller than the nucleus radius. This is accounted already into the dipole proton cross section, but there the lifetime is bigger than the proton. So we resum all these interactions a lot of times. But here in the nucleus, we will have a smaller interaction, since we will have less interactions than the A multiplied by the dipole cross section. So we will have a reduction of the gamma A cross section compared to A times the gamma proton cross section. And this will be called the gluon shadowing effect. And since this effect is related to the gluon radiation, the best way to describe this is by renormalizing the QQ bar cross section. So we will multiply the dipole cross section by the suppression factor, the RG factor. We did this in a previous work, but we did for heavy vector mesons. There we calculated that RG factor with the PDF EPPS 16, and we used a factorization scale of the mass of vector meson divided by 2. With this approach, we got a good description of the available data for psi1s with 2.66 TV and 5.02 TV. However, when we consider light vector mesons, we don't have an X scale that is small enough to be used into this case, because the PDFs are calculated with fits of the F2 structure function and they are evolved with the Diglep equation. So the collaborations just have currently distributions for scales higher than the mass of the charm, that is 1.3 GeV. So we have a problem. We don't have gluon shadowing well enough for the light vector mesons. So we found a way to extract the gluon shadowing. We did it effectively by fitting the available data for the whole vector meson production and one data point of the F2 structure function for on a scale that is appropriate with the scale of the whole vector meson, that is 0.15 GeV squared. So we minimized the results for all these 5 data points, and we got an optimal value for the gluon shadowing that is 0.85. So with this value, we found results for the whole vector meson, that is these curves here. This is on the ground state. So we could describe the 4 data points available for this vector meson, and we could calculate with the same approach, but with some modifications, because this is a DAS structure function. We got 0.53 for the ratio of the nuclear structure function for the proton structure function. That is inside the error bars here in this point. The success of describing this data motivates us to make some predictions for other vector mesons. So we did predictions for the omega vector meson and the phi vector meson with the same RG factor and the same setup that I explained before. So we did this because future measurements of these quantities could bring some information about the dependence of the RG into the scale, because especially for the phi vector meson, because since its mass is more different from the whole vector meson, we can see if this RG is good for another vector mesons. We also made predictions for the ratio of the excited state cross-section to its corresponding ground state cross-section here. And the importance of these results is that this ratio is very sensitive to different dipole cross-section models. So here we use GBW model, but if we use another one, we will get very different results. So if we got these measurements, we could see which is the best dipole model to describe this kind of data, which is a very difficulty in our search, because there's a lot of models and we didn't found one that could describe a lot of process all in the same time. And it also probes the vector meson wave function in some kind of way, but it's more sensitive to the dipole model cross-section. So this is it. So basically, light vector meson photo productions needs a small hard scale. We use the Glauber-Gribov approach to calculate the cross-section for nuclear targets. With this approach, we need to include the gluon shadowing effect, and this is done by the RG factor here. Use fitting the 4 data points for whole 1S UPC data from the Alice collaboration and the data point from for F2 data, we got an effectively factor of 0.85, and the success of describing these 5 data points with this RG made us make predictions for other vector mesons, like the whole 2s, the omega 1s and 2s, and the phi on the ground state and excited state. And we also made predictions for the ratio between the excited and ground state cross-section, because it depends on the vector meson wave function and can be a good probe for the dipole cross-section models. If you want to see more about the production of light vector mesons with nuclear targets, you can see the poster of my colleague Jaimo that is on the coffee break. And this is it. Thank you very much.
Thank you. Now it's time for questions. Oh,
Thank you very much for your very nice seminar. Would it be possible to use the same approach to look at the cross-section for production of heavy vector mesons or heavy light vector mesons?
Yes, you can use the same approach, but we need to change the vector meson wave function, because it has some approximation to find this form of wave functions that is not very suitable for heavy vector mesons.
Just the wave function, not the other part of the calculation.
Yes, just the
Okay.
wave function.
Okay, thank you.
any further questions?
Did you check that your wave function of the rho meson was good to reproduce the decay with?
No, we didn't check decay.
It's one of the things that you do when you are, finding the wave function. I think that the people that started this, you quoted Brodsky and other people, so probably they did that. It's just a check.
Yes, we checked cross sections with proton target, but not decay width.
Okay, any further questions? Rogerio? Okay.
Thank you. Is there anything that you would like to see measured? For example, the question of the heavy quarkonia, because we could produce them in different target sizes. We can't control the length at which the formation happens, so it's all these arguments. But do you see any usefulness in measurements of J psi, for example, on nuclear targets, to kind of check maybe your model, or you think you could check it on other things and you don't learn that much on the J psi? Because you say this, the model you are using for this dipole interacting across nucleons is kind of under control. I'm just wondering whether
We did previous work with J psi photo production, and then we can check more about the dipole model and the gluon shadowing too. Here I specifically studied the light vector mesons, because then we have difficulty about the vector meson wave function and the small scale. So yes, there is a lot of interesting of studying J psi too.
Any further questions? Actually, I have questions. So you said the higher states have smaller lifetime, the QQ, the dipole. So
Yes.
why is it so? Why the higher states like the QQ bar G has a shorter, let's say?
They are heavier because the the photon splitting into the QQ bar is just the first state. We have just two particles, but then with gluon radiation, we will have three, and this gluon can have some transverse momentum.
But the gluon is massless. It can also have, let's say, very little transverse momentum.
Sorry, I didn't
The
understand.
gluon is massless, so it can also have very small transverse momentum.
Yes, it will be a soft gluon.
Yeah,
very
right. In
small.
that case, the lifetime would not be much smaller, right? But for soft gluon.
Yes, but in Kopelevich calculations, he showed that the lifetime will be smaller for the high.
Even for soft gluon.
Yes.
Okay, I see. Okay. Thank you. If no further question, let's thank Sarah again. Let's now move to the last speaker of this session, Bruna de Oliveira Stahlhofer. So she will talk about double parton scattering in ultra-peripheral collisions. Let's start.
No. Oops. Where is the pointer?
It's bad, it's pointer.
Ah, okay. But also, but I think if I press here,
it will not
goes to another slide.
No, well, no.
Okay, sorry. So good afternoon, I'm Bruna. First, I would like to thank the organizers to the opportunity and in special for the ENCT support. Now I'm going to talk about the work I have been done during my PhD involving double parton scattering in ultraperipheral collision in collaboration with Edgar and my advisor, Professor Emmanuel. First, I'm going to give you some very quickly and general picture of ultraperipheral collisions and double parton scattering. Then I'm going to talk about some specific process and how we built a specific procedure to evaluate the GPS cross-section for that. Then I'm going to show you the work that we just are doing right now. Then I show you some very preliminary results and some perspectives. So in ultraperipheral collisions, we have the distance between the center of the nuclei, or in other words, the impact parameter, larger than the sum of the radii of the nuclei, could be also a nucleus and a proton. And the photons are interacting here, are radiated by an ultra-relativistic moving charge. This is hard, sorry. So we call these photons elastic photons, or also quasi-real photons. This means that the interaction is predominantly electromagnetic one, but unless we consider the nucleus out to break or dissociate, then we can probe parton distributions inside the nucleus. So double parton scattering, we have two final states produced in the same collision, and the interactions are independent to each other here. And the way we evaluate a GPS cross-section is through, we roughly call a pocket formula. Here we have the two cross-sections, SPS, simple parton scattering, for both of final states, divided by, we call an effective cross-section that has dimension of cross-section. Then we restore the cross-section dimension for that formula. So maybe some of you can remember the seminar gave by the Professor Emmanuel on Tuesday. He talked about pocket formula, then he showed to you some experimental results for the effective cross-section and highlighted some disagreement between such measures then talked about some reasons for that, and then went through correlations and so on. But all that considerations were thought for central collisions. Here we are talking about ultraperipheral collisions. So the photons are interacting here, carrying some energy fraction from the source, and the flux of such photons has dependence on such energy fractions, and all of that must to be taken in count when we evaluate a DPS cross-section. So before we just start thinking about any kind of correlations, we just need to figure out how to build an effective cross-section that works for an ultraperipheral collision. And this was done for the first time for the collaborators of this work. So let's look some specific process. Here we choose the mu and a CC bar final state. Why this should be a good choice? Well, the mu is produced by two photons coming from two nuclei, lead nuclei. So this cross section goes with Z square, and combined with the CC bar, we take a gluon already in leading order. So if we look to SPS contribution to the same final state, we need to go to next to leading order, etc. And we can guess that the DPS contribution is not suppressed by SPS1. And if we choose the right cinematic variables, maybe this is reasonable to measure in an experiment. The another reason to this choice is we are taking a gluon from the target, so this target is going to break, and we are taking a photon also from the target. So we can prove the correlation between them that, for instance, we consider none, but in the near future, maybe if some experimental measurement shows disagreement with our results, so we can look again for that. So here is general equation to the double particle scattering. Let's see some of these ingredients. Here we have the photon flux, the flux of photons 1 and 3 coming from the projectile, with dependence on, of course, the energy fraction and the impact parameter of such photons. And here the parton distribution of the photon and gluon coming from the target, also with the such dependence. And here these variables can be changed to get differential in rapidity, in invariant mass. And here this half side function is to guarantee that is a ultraperipheral collision. Of course, the partonic cross-section level here. So let's look to the correlation between such partons. In high energy limits, the photons coming from the projectile is reasonable to think that they have no correlation between them. Here, this half side function is just saying for us that the photon is outside the target. And here, as I told you, we are considering no correlations between the photon and the gluon in the target, but it's not a straightforward conclusion. But where is the effective cross-section here, right? Maybe we can pick the photon 1 from the projectile with the photon 2 from the target, put together and integrate over the impact parameter of the photon that is going to produce the mu. Then take the photon 3 with the gluon distribution, just with the dependence on the impact parameter, because we are going to assume they factorized here too. And also integrate over the impact parameter of the photon. So just, let me just divide it by the total flux of photons here and here. Then we can think about this equation as a measurement of how many partons are available to interact. So here is our analogy to some kind of thickness function, one for the two photons producing the mu, and one for the photon and gluon producing the CC bar. Then put it together and integrate over all the total impact parameter. We can define the effective cross-section as the inverse of that equation, because we want the effective cross-section denominator. So take all that another elements left behind here. Maybe you can be confused, but trust me, all the elements are here, but multiplied by the total flux of photons just to cancel, this one. We put here to take some physical meaning for that. Then we recovered that general formula I showed before, and we can think this as partial cross sections, and divided by the effective cross section, we recovered completely that general relation. So this is our equivalent pocket formula. It's not so trivial, but can be done. Our numerical results. Here, the smallest value for the effective cross section is where the photon 3 is found more easily inside the target nucleus and available to interact with the gluon. And for small or too large values of Xi, the photon rarely overlaps with the gluon, so we get larger effective cross-section values and smaller DPS cross-section. The total results going with the charming rapidity. Here we plotted the contribution of inelastic photons just to show you that they not contribute so much to the total result. And here, if we take a projectile, not a nucleus, but a proton, so the picture changes and the inelastic photons contributes more. And we have in order of picobarns, smaller than this one nucleus in nanobarns. Here just to show you the shape of the cross-section of a simple scattering producing the muon. We see some asymmetry because we are taking two photons from the projectile and a photon gluon for the target. But when we look to the DPS cross-section, the asymmetry is much larger, just because the dependence of the effective cross-section on the energy fraction carried by the photons in the initial state. So this illustrates that DPS is not a simple rescale of the SPS, or in other words, the effective cross-section can't be just a constant value. Okay, so what now? What could be our next step? Well, we can think about some observable that is measured with more accuracy. Maybe we can think about J-PSI production. But when we think about J-PSI production, a lot of issues came in mind. First, for example, if we are going to build an effective cross-section, say, for a double J-PSI production via DPS, we want a partonic level interaction. So here, we can't use a dipole model or even consider the apomeral exchange. And but okay, can be done also. The simplest way is using color evaporation model in leading order. And also, if we take a gluon from the proton, this proton is going to break. So this is the dissociative J-psi. For that previous procedure process I just have showed now, there is no experimental measurement. But for this one, well, it happens that there is. Just on April this year, Alice published this paper mentioning the J-psi photoproduction in a proton-nucleus collision and ultraperipheral collision. And for the first time with the proton dissociation. So very exciting news. It's not a DPS mention, but it is something. And here, actually, Alice added just 2 experimental points to the cross-section. The other points are from Hera, but by means of electron-proton collisions, and they have another channels. Alice actually just detected the muons produced by the J-psi decay. And here is our curve, our results, in more agreement with the other results. But when we integrate the cross-section over this specific range of rapidity, we get this result to the cross-section for the dissociative J-psi in microbarns. And this is the Alice result. So it is slightly surprising agreement because we used the simplest model here. And also a plot for the cross-section considering the flux of photons, so not photon proton, but nuclear proton here, and with proton dissociation going with rapidity. But now, if we are going to think about double J-psi production via the GPS, we can make some questions like, is this dissociative J-psi predominant over the exclusive one? So that paper tried to answer that. Here is a result showing the ratio between the dissociative J-psi and the exclusive one. So Alice got a result that shows the dissociative J-psi is larger, but not large enough to say that they predominate. But then we can make another question. Is it possible to distinguish the dissociative J-psi from the exclusive one? And they tried to answer that too. Here is the muon count produced by the decay of J-psi. And for this region in transverse moment, almost all the contributions is from the dissociative J-psi. And just for a very short range of PT, the exclusive production dominates. So yes, they can distinguish between them. Of course, these add some error in the results, but again, it is something. And now, our very preliminary results, the effective cross-section for 2 dissociative J-psi produced by via DPS, and here the DPS cross-section going with the rapidity of 1 J-psi and fixed 3 values, 3 different values for the another J-psi. But actually is in order of femtobarns, a little smaller than we naively expected, but we can improve that. It's just a preliminary result. And also we can consider it a dissociative J-psi and an exclusive one, because at least the DPS cross-section is going not to drop for a half, because then we have 2 different final states. But beyond all the improvements that can be done here, another thing is if you look with a little more attention for the title of that Alice paper, they not just measured the dissociative J-psi, also they measured the exclusive D-muon produced by in a proton nucleus collision. So here are the results by Alice, and here is a plot coming from the specific PDF, considering just elastic photons. So they achieved this experimental point here, which is good because the error bar is smaller here. Here no one achieves, and this one, our curve is better, but also have a larger error bar. So a lot of things to think about it here too. But why not? We can think about a final state with dissociative J-psi and exclusive D-muon via DPS. So let me do some conclusions. So we have explored the photons density inside the nucleus in ultraperipheral collisions and the correlation with the gluon's density. We have evaluated for the first time an effective cross-section for 3 photons and 1 gluon in the initial state in UPC. We have found a measurable double particle scattering considering the LHC and FCC and maybe AIC too. With these new experimental results from Alice, we are able to test our procedure and make new predictions. Also, maybe our results can be seen as experimental motivation for near future measurements involving double particle scattering in ultraperipheral collisions. So thank you very much.
Thank you, Bruno. Now it's time for questions.
Can I look at the slide 13? This might be a very naive question, but I'm just curious.
What slide?
13?
13?
Oh yeah, this one.
Yeah.
So I was just curious. This might be a very naive question, but J-psi, as I understand, you mentioned about dissociative J-psi and
Yes.
the exclusive J-psi.
Yes.
Both of them are color singlet, isn't that right?
Yes.
So I wonder about this single gluon attaching to the color singlet.
Yes. Actually, using the color evaporation model, we don't look to the octet of the color octet.
Yeah.
Just to
Yeah, that's right.
Yes.
So it might be much more involved just to this. I think this diagram itself, it doesn't really.
Yes, but
sense.
actually this simple model described it very well.
So when you actually do the calculations, you have this, what do you do? I mean, you consider color octet?
No, just the color evaporation model, where we integrate over the invariant mass from the mass of J-psi until the 2 times the mass of meson D. And of course, there is some factor, just 1 per 9.
Yeah, I was wondering
of
about,
that
yeah,
is going to form J-psi, and another is just CC bar open.
but one can also think that before J-psi is formed, you may have 2 gluons attached to make a color singlet.
But that could
Then
be
it's a high
exclusive, right?
voltage, right? Of course, the coupling will be different. So that's what I'm asking.
But then could be exclusive, right? If we take 2 gluons. Oh, okay, okay.
I think this color. I think this color evaluation model doesn't care about the color degrees freedom, right? You just calculate this 60-part pair, and somehow it's with a kind of conversion coefficient, it directly produces JSI, right? You don't track whether it's color singlet or octet,
No.
right? So I think this is just the color evaporation model. Yeah. This is a very crude model. Yeah. But it worked miraculously well.
And maybe just a comment, there will be soft glue interactions after that will make the JPSI singlet, right? And they factorize. This will be taken into account in the factor we put in front of the calculation. So there is a factor in front of the calculation, it's factorizable. Well, if you put, can you put please again the diagram? It will be the diagram 13. Yes, it will be on that ellipsis there somewhere. Right, but yeah. But it's no. Then it's exclusive. Yes. Yes.
Okay. Any further questions for Bruna? Okay, maybe I have a question. I have a maybe very naive question. So you see, you basically this is let's say single parton scattering SPS, right?
Yes.
So basically your title is basically double parton scattering. So what is let's say because I think the double parton scattering would have a much smaller cross section or lower chance compared to single parton scattering.
Yes,
so what is the motivation to study double parton scattering? Maybe you mentioned that, but I missed this.
Yes,
Sorry.
because we can think that the double parton scattering must be considered in some regions of cinematics. Actually, they can make some difference. But yeah, our preliminary result is very low, but also we can have some insight about the parton distribution looking for the double parton scattering.
Okay, so essentially you would like to measure kind of the double parton distribution function in this in the nuclei. So you want to so basically what kind of, my question is essentially what kind of information you can extract through double parton scattering which cannot be extracted from single parton scattering?
Oh yes. For example, when we construct the effective cross-section, we take information about correlations between the partons that are available to interact. And we can prove that just looking for the DPS cross-section. And maybe with considering the muon together with the dissociative JPSI, we can get some DPS cross-section that is more available to be measured in an experiment. And then we can take some conclusions about what is happening for example, in the distribution of the photons inside the nucleus, or the proton in this case.
Okay, so in this case, basically the correlation between two photons or between one photon and one gluon.
Yes.
Okay.
On the target that is allowed to break, so could be a proton in the case of double JPSI, or a photon gluon in the case of the muon dissociative JPSI.
Okay, I see. I understand. Okay, thank you. Okay, any further questions for Bruna? So if no more questions, let's thank Bruna again, and we should also thank all the speakers in this session because I think no more speakers, right? So now the session is closed. 7:30. Okay. 7:30. Okay. Very nice talk.